Here's something no one tells you. Every massive structure you see rising from the water, every bridge piers, every offshore platform, every dam, every wind turbine bolted to the ocean floor, almost none of it was built underwater. They built it in the dry. The whole game of underwater construction, the trillion-dollar industry, the 200-meter deep foundations, the structures that take decades to complete, it all comes down to one question that nobody asks. Before you build anything, how do you get rid of the water? And the answer is one of the most brutal, dangerous, and quietly brilliant engineering solutions in human history. Let's say you need to build a bridge pier right here in the middle of a river. You cannot just pour concrete into water. It will not bond to the riverbed. It will wash away. The current will destroy it before it sets. So engineers build something first, a temporary structure that was never meant to survive. It is a temporary enclosure. They call it a cofferdam. It starts with sheet piles, thick steel plates, each one interlocking with the next, driven into the riverbed one by one, not hammered down, vibrated down. The machine liquefies the soil around the pile just long enough for it to slide in, then the ground tightens around it like a fist. You keep going, sheet pile after sheet pile, until you have built a steel wall that encloses the area where the foundation needs to go. Then you pump the water out, and this is where engineers get their first nasty surprise. The moment you lower the water level inside the cofferdam, you create a pressure difference. There is still full water pressure pushing on the outside, and nothing pushing back from the inside. The wall wants to collapse inward. In 2004, during the construction of a major highway interchange in the Netherlands, a cofferdam failed exactly this way. The walls buckled. The site flooded in minutes. Nobody died, but only because the crew had drilled the evacuation protocol until it was reflex. The fix is a bracing frame, a steel skeleton bolted inside the wall, holding it open like ribs. But here is what they do not tell you in the textbook. Even a perfect cofferdam leaks. You pump the water out, and water comes back in, not through the walls, through the ground. The pressure difference does not just push on the steel, it pushes water up through the soil beneath your feet like a slow, cold geyser. Workers stand on what looks like dry ground, and it is wet, and getting wetter. So how do you seal a floor you have not built yet? You flood it, on purpose. This sounds insane. You spent weeks building a wall to keep water out, and now you are letting it back in. But here's the thing about concrete that most people do not know. It does not need air to cure. It needs chemistry. Concrete is denser than water. If you pour it correctly, slowly, without turbulence, without letting water mix into the paste, it will sink, set, and harden at the bottom of a flooded pit just as well as it would on dry land, sometimes better. The water actually keeps the concrete from drying too fast, which can weaken it. The tool they use is called a treme pipe. It is a long, segmented tube lowered to the bottom of the flooded cofferdam. They fill it from the top with specialized concrete. The key, the thing that makes this work or fail, is that the discharge end of the pipe stays submerged in the rising concrete at all times. The concrete pushes the water up and out. It never mixes. If you pull the pipe too early, water rushes in. The concrete is contaminated, the seal fails. And if that happens after you have pumped the site dry and started building the foundation on top, the whole thing can flood without warning. That happened. So you wait. You let the concrete cure, and then finally you pump the remaining water out, stand on your new concrete floor, and build like you are on dry land, hundreds of meters below the surface of a river. But all of this only works if the water is not too deep. Cofferdams max out around 30 to 40 meters. Below that, the pressure is so intense that no steel frame can hold the walls open. For 150 years, that depth was the wall. Engineers built up to it and stopped, until they decided to try something that should have killed everyone involved. New York City needs a bridge across the East River, the largest suspension bridge ever attempted. And the foundations need to go down through 24 meters of water and soft riverbed, all the way to bedrock. No cofferdam can reach that deep. So the engineer, a German immigrant named John Roebling, designed something new. A wooden box, the the size of a gymnasium, sealed at the top and open at the bottom. It is lowered to the riverbed. Compressed air is pumped in, enough pressure to hold the water out, like turning a cup upside down in a sink. Then workers climb down inside. Inside the caisson, the air pressure is 3 times normal. It is hot. It smells like sulfur. The gas lamps burn a strange color. Workers dig out the mud and rock by hand and hoist it out through pressurized airlocks. As they dig, the whole box sinks deeper into the riverbed under the weight of the masonry being built on top of it. They work in shifts. They surface. They go home. And some of them never walked again. Nobody understood what was happening at first. Workers would surface and within hours feel crushing pain in their joints. Some lost the use of their limbs. Some died. They called it caisson disease. They thought it was bad air, bad food, weakness, decompression, sickness. The compressed air forced nitrogen into the workers' blood. When they surfaced too fast, it came out of solution as bubbles inside their muscles, their joints, their spines. John Roebling's son, Washington, took over as chief engineer when his father died. Washington himself descended into the caissons to supervise. He got caisson disease. He was bedridden for years. He directed the completion of the Brooklyn Bridge from a window in his apartment using a telescope and written notes relayed by his wife. The bridge opened in 1883. It stands today, and it was built by men who had no idea they were slowly being killed by the air they were breathing. By the time engineers understood the mechanism, the caisson era was ending, not because of the deaths, because they hit another wall. The deeper you go, the higher the pressure. High enough and nitrogen narcosis sets in. Workers hallucinate. Beyond that, oxygen itself becomes toxic. There was a hard ceiling on how deep a human being could work inside a pressurized box. And the ocean floor was much, much deeper than that. So the 20th century did what engineers always do when humans become the bottleneck. They took the humans out of the equation. The drilled shaft changed everything. No cofferdam, no compressed air, no workers underground. A drill bores down through the water column and into the seabed, sometimes through 200 meters of ocean before it even hits rock. A steel casing follows the drill, lining the hole. Then steel reinforcement is lowered in, then concrete pumped through a tremie pipe, just like before, but now at depths that would crush a submarine. No dewatering, no pressure chambers. The water does not need to leave. The concrete just displaces it. In the North Sea, off the coast of Germany, engineers used this method to build one of the largest offshore wind farms ever constructed. 67 turbines. Each foundation, a hollow steel pile, 85 meters long and 8 meters across. Weight over 1,300 tons. Transported by barge. Positioned by GPS. Driven into the seabed by a hydraulic hammer that hits with 1,500 kilojoules of force per strike. And the vibration trick from the cofferdam days still applies here. The hammer doesn't just push, it shakes the pile as it descends, momentarily liquefying the sediment around it, letting the steel slip through, then the ground closes in and grips it like concrete. Each pile placed to within centimeters. In open ocean, in North Sea weather, where a storm can arrive in an hour and waves hit 6 meters without warning. It took 23 months. The farm now powers 400,000 homes, but drilled shafts have their own ceiling. They anchor to the seabed, and in the deepest parts of the ocean, where the most valuable resources sit, the seabed is 2,000 meters down. You can't drill a foundation shaft 2 kilometers deep. The engineering math doesn't work. The materials don't exist. So for those depths, engineers had to abandon the idea of touching the bottom entirely. The Appomattox platform sits in the Gulf of Mexico in 2,300 meters of water. It is 29 stories tall, 2 football fields wide. It weighs more than an aircraft carrier, and it doesn't touch the bottom. The platform floats, held up by its own buoyancy, but floating structures drift. In a hurricane, an untethered platform the size of a city block becomes a missile, so engineers anchor it, not with a rigid foundation, but with steel tendons. Cables essentially run from the bottom of the platform down 2,300 meters to anchor piles driven into the ocean floor. The platform pulls upward. The tendons pull down. The tension between those two forces holds it in place. It moves. It is designed to move up to 10 meters in any direction. It flexes and sways. In a major storm, you can feel it. 400 people live on it full time. But the engineering problem that almost stopped the whole project was not the structure. It was the pipes. The platform needs to connect to the wellheads on the ocean floor, 2,300 meters below. Those pipes, called risers, run through water that sits at 2 degrees Celsius under crushing pressure, and they flex with every movement of the platform above them. Every wave, every current, every slow oscillation of a structure the size of a city block. The insulation on those pipes had to survive 40 years of that. No existing material could do it. The engineers had to call in chemists. They developed a new polymer, tested it, failed, reformulated, tested again. The project was delayed over it. The construction of the topsides, the 4 modules that form the working platform, took 2 years and required placing 10,000-ton sections with 1 centimeter precision. A crane that can lift 10,000 tons and position it to within a centimeter does not exist as a standard tool. They built custom equipment for the job. Total build time, 6 years. Total cost, over $4 billion. And it is designed to produce oil for 40 years, twice as long as any platform before it. But here's what nobody thinks about when they see an oil platform or a wind farm or a bridge pier rising from the water. All of that technology, the cofferdams, the caissons, the drilled shafts, the floating platforms, was developed to project power outward, to extract, to connect, to expand. Some of it gets built to hold the line. On Hayling Island off the southern coast of England, the coastline was collapsing, not slowly, measurably. Year by year, the sea was eating the shore. 1,800 homes sat behind it. Some had been there for 100 years. There was no offshore resource to extract, no bridge to connect, no platform to justify a billion-dollar budget. Just families. The project cost $6.5 million, a rounding error in the world of offshore engineering. They imported 70,000 tons of rock from Norway, granite specifically, dense enough to resist wave force, and built a revetment 650 meters long along the shoreline. Then they spread 25,000 tons of pebbles across the beach to absorb the energy of incoming waves before they hit the rock. 6 months of work. Tidal windows of 4 hours at a time, twice a day, when the water was low enough for the machines to operate. It will protect those homes for 100 years. And if you pull all the way back from that beach in England to the Gulf of Mexico, to the North Sea, to the East River in 1870, a pattern appears. Every breakthrough in underwater construction happened because the previous solution stopped working. Cofferdams hit their depth limit, and engineers invented the pneumatic caisson. The caisson started killing workers, and engineers invented the drilled shaft. The drilled shaft ran out of seafloor, and engineers invented the floating tension platform. Each generation pushed further. Each generation paid a price, in money, in time, in some cases in lives, to find out where the new limit was. Washington Roebling lay in his apartment watching the bridge he'd been broken building, and he knew something that every engineer who came after him figured out eventually. You don't conquer water, you don't beat it, you negotiate with it, a little further each time, for a little longer, with a little more precision than the last generation could manage. The ocean doesn't care about your deadline, it doesn't care about your budget, it doesn't care about your legacy, it just keeps moving, and so do we.